Welcome to this short course on understanding large language models, presented by Dr. Microlearning in January 2026. Over the next few minutes, we'll unpack what LLMs are, how they work, why they matter, and what challenges and opportunities they bring, so you can get a clear, practical picture of this important AI technology. This slide outlines our journey. We'll start with an introduction and core concepts, then explore architectures and practical applications, before discussing challenges and the future of LLMs. Think of this as a roadmap to guide our discussion and help you connect each piece as we move through the material. Let's begin the first section, an introduction to large language models. I'll give a concise overview of their core purpose, the kinds of tasks they handle, and why the underlying neural architectures make them so effective, setting the stage for more detailed concepts and examples in the next slides. In simple terms, large language models are AI systems trained on vast text collections to understand and generate human language. They're versatile, handling translation, summarization, sentiment analysis, and dialogue, and they rely on advanced neural architectures like transformers to capture complex context and produce fluent, coherent outputs. LLMs play a key role in modern AI by acting as a communication bridge between humans and machines, lowering technical barriers and enabling natural interaction. They also automate repetitive tasks such as customer support and data processing, improving productivity, and they expand accessibility through tools for content creation, language learning, and assistive technologies. The historical development of LLMs moved from symbolic AI and early statistical models to a revolution in 2017 with the transformer architecture. Since then, innovations in scale, bigger models, more data, and refined training have driven rapid improvements in capability and versatility across many applications and domains. Now we'll dive into the core concepts that make LLMs tick, focusing on the neural foundations, the role of large datasets, and how fine-tuning and reinforcement learning shape model behavior. These building blocks explain both the strengths and some limitations we'll discuss later. At the heart of LLMs are transformer neural networks that use attention to model relationships between words efficiently. Deep architectures stack many layers to capture complex patterns, and representation learning produces contextual embeddings so the model can associate word meaning with surrounding text and nuanced usage across contexts. Training on massive, diverse datasets helps models generalize across domains and linguistic styles. By parsing billions of examples, they learn grammar, sentence structure, and world knowledge. While tokenization breaks text into smaller units, the model uses to predict and generate language with structural coherence and meaning. Refinement comes from fine-tuning and reinforcement learning, which align models with human preferences and safety norms. Targeted fine-tuning tailors performance for niche tasks like legal or medical text, and methods like reinforcement learning with human feedback help shape behavior toward more helpful, context-aware, and ethical responses. Next, we'll look at the architectures behind LLMs, highlighting why design choices like parallel processing and attention mechanisms matter, and how different encoder-decoder setups affect performance. This gives a clearer view of the technology decisions that impact capability and efficiency. The transformer architecture replaced recurrent models by enabling parallel processing and scalable training, which unlocked much greater capacity. Its multi-layer encoders and decoders balance feature extraction, context understanding, and output generation, while positional encoding preserves order information despite parallel computation. Encoders process input text into rich, high-dimensional contextual representations, while decoders use those encodings to generate meaningful outputs tailored to a task. Some models employ bidirectional encoding, which reads context from both directions to capture nuanced relationships and improve comprehension in tasks like understanding and classification. A key innovation is the attention mechanism, which scores relationships between words using a query key value system. Self-attention lets the model weigh dependencies within a sequence to build contextual understanding, and scale dot product scoring balances computational efficiency with reliable mapping of relevant context for each word. Moving into applications, LLMs power a wide range of real-world tasks from language understanding to problem-solving. In this section, we'll survey common uses both consumer and enterprise, including how these systems improve workflows and create new capabilities across industries. In natural language processing, LLMs enable text analysis like sentiment detection and summarization, provide context-aware translation across languages, assist with content generation for articles or reports, and streamline text classification tasks such as filtering, categorization, and detecting misleading or harmful content. Chatbots and virtual assistants benefit from LLMs through more personalized, context-rich interactions that adapt to user preferences. They offer real-time assistance to reduce wait times, automate routine tasks like booking or reminders, and support communication in many languages to broaden accessibility for global users. LLMs also assist developers with code generation and problem-solving by producing functional snippets, suggesting fixes to buggy code, proposing algorithmic approaches for complex tasks, and offering learning support for beginners through explanations, practice tasks, and insights into programming frameworks and best practices. Now we'll explore the challenges and limitations that come with LLMs, from technical constraints to ethical concerns. Understanding these issues helps us balance enthusiasm with caution and points toward areas where research and policy need to advance. Training and deploying advanced models is resource-intensive, requiring significant compute and energy, which raises environmental and cost concerns. As datasets and model sizes grow, scalability becomes more complex and expensive, and real-time systems may face operational delays that affect user experience and responsiveness. Ethical concerns include algorithmic bias that reflects skewed training data, risks to data privacy from large-scale data collection, and gaps in accountability when models produce harmful or unintended outcomes. These areas often fall into regulatory gray zones and demand clear responsibility and oversight. Another major issue is hallucination, where models generate plausible-sounding but factually incorrect information. Performance can vary across domains and languages, undermining reliability, and the opaque nature of deep models makes identifying and correcting errors a persistent technical challenge. Looking ahead, the future of LLMs will be shaped by trends in personalization, deeper integration with real-world applications like healthcare and education, and a stronger emphasis on ethical AI. These directions aim to make models more useful, safer, and better aligned with human values and needs. We can expect enhanced personalization as systems adapt to individual preferences while maintaining privacy protections, tighter integration of AI into industry workflows to boost productivity, and growing focus on fairness, transparency, and reduce bias as part of responsible development and deployment. Protecting user data, mitigating representation bias, and preventing misuse are central priorities going forward. Practically, this means building safeguards against malicious applications, enforcing privacy-preserving practices, and continually improving model fairness and inclusivity to build public trust in these technologies. Sustainability will also guide development, with efforts to reduce energy consumption through more efficient models, optimize infrastructure for scalable deployment, and promote environmentally conscious practices so AI progress doesn't come at undue ecological or financial cost. Integration with other technologies opens new gains. AI-driven IoT can improve energy efficiency and enable predictive maintenance using analytics, while automation enhances operational workflows. Combining LLM capabilities with sensor data and connected systems unlocks smarter, more adaptive applications across industries. Cloud and infrastructure strategies help ensure scalability and accessibility, allowing AI services to reach users globally while handling heavy processing demands. Strengthening data storage and processing pipelines in the cloud supports secure, large-scale model operation and consistent performance across regions and use cases. Edge computing and on-device capabilities reduce latency by processing data locally for faster responses and real-time analysis, enhance privacy by limiting sensitive data transmission, and improve device independence so users can access AI features even with intermittent connectivity. Ethical AI development should prioritize equity, so systems treat users fairly and avoid discrimination, while privacy protection demands robust security and data handling practices. Transparency in documentation and explainability is essential to maintain accountability and public understanding of how models make decisions. Regulation and oversight will require compliance with legal frameworks at global, regional, and national levels. Constant monitoring to detect improper use or harmful behavior, and adaptive policies that evolve alongside technological advancements to ensure safe, reliable deployment. Broad societal effects include economic shifts in job markets that require thoughtful workforce transformation, ensuring accessibility so AI benefits a wide range of social groups, and building trust through consistent safety, reliability, and inclusive design to sustain long-term adoption and value. Thanks for watching this overview of large language models. If you'd like to explore any topic in more depth, architecture, training, applications, or ethics, feel free to continue the conversation, and I'll guide you through practical examples, demos, or further reading to deepen your understanding.